in time travel debugging, we allow somebody to record the execution of a program from the process level down to the instruction level of the CPU, the whole thing. And then this can be replayed on your own time by a colleague, by your vendor, by your customer, in their own machine at their own pace. And they can go backwards in the recording. So if you've recorded everything, the crash is at the end of the file, load this file, go to the end of the recording file, and go backwards. So you can trace everything as is. But we're here to talk about HLS. So we realized that today, HLS is essentially a subset of C or C++, right? System C, System C++, all the different models, either you make or you consume. And obviously, it's very widely used. In fact, C, C++ is very widely used. All the EDA companies you see out there, they're all building something or the other in C or C++. So we are aware that in the semiconductor industry, C, C++ is being used. HLS and other things are being used. But why are we not using the tools used by software industry in this hardware industry of ours, right? We are still relying on a lot of pen papers, EDA tools, and whatnot. And also, obviously, banging your head on the wall. That sometimes works, but sometimes it does not. So there are verification tools that will help you with coverage, memory, functional verification, sanitizers. But what about tracing what went wrong? I don't think anybody's doing that, and that's where we come in. So today, if you see, in the traditional debugging, once a bug is discovered, there's a lot of logging that's done. You want to see, you put printfs, couts, whatever is your flavor. You try to get some dumps because a lot of these libraries are multi-threaded, parallelized, or you even try to get a debug build from the library developer. And sometimes that helps, sometimes it does not, and it takes a lot of iterations of going round and round until you actually bang your head against the wall. And sometimes that does work, but most of the time it does not. And that's where we come in. So we've come up with a reliable methodology called record, replay, and resolve, right? Record the execution of your Linux process, your program, your systemc model. We are smart enough to intercept if something happens. We stop recording, we save the recording as is. Take this recording to our debugger UDB, which is the time travel debugger, which goes both ways, backwards and forwards. So as I said, there's a crash, we stopped recording, so that crash is at the end of the file. Now you load it in the debugger, go to the end, and go backwards from the symptom to the problem. And that's how you resolve it. Before I go further, I want to show you guys something. Or let me say, I want Claude to show you something. And this is normally not a part of a DVCon presentation, but thank you so much, Rafael, for allowing me to do a live demo, and that to not me, but the AI, right? So we ran this test just now, and as you can see, there are about 2 fails, right? And something failed. This was a test with a lot of systemc libraries, and now I don't know which library, or in fact, even if we find out which library, what did the library do wrong? How do I find that out? So what I did, I recorded the test. Simple code, but in interest of time, I'm going to just load the recording in UDB as is, and I promise I just made this recording. So as you can see, we have this recording, and we are at 93% of the code execution already. So I'm going to go to the start of the recording, and I'm going to enable Claude. So this explain library creates an MCP server of our debugger and gives any coding agent or assistant that you might be using access to my recording and my debugger, but only in English. So let's say, explain what went wrong with this program. And now this is going to be really tricky because sometimes it takes a minute, but sometimes it takes 5. So let's see. Let's see if I get called out on the timer or not before it does. So it's already quantum leaping. I'm going to try to explain you some of the steps as it traverses.
No,
yeah. Right, so it went to the end in the beginning. As you can see, you went. And it did a back trace just now to see if you can actually guess what could have happened, right? And we have this amazing feature called bookmarks. So when you're in a long debugging cycle, you lost track of where you were, where you want to go back. So there are a lot of bookmarks it can make. It does even further back traces. Prints a few things to try and analyze what's going on. By the way, the problem, I'm going to just tell you right now before this finds out, the problem generally is that it's picking the wrong bit from an array. It's picking bit number 1, it's supposed to pick bit number 0. So I've asked it to go find out if it can tell me the exact same thing. Also, as you can see, this is this reverse finish command, which basically unwinds time. It takes you before a function, like finish takes you after a function call finishes, this takes you backwards. And it actually unwinds time. Now it's already found, it's gotten into my main from the last, and now it's using reverse next, which is step 1 line back. And again, another bookmark, because it wants to keep track of where it's gone and what all it's doing. Now, this is very interesting over here. Last value. So we have this magic command called last. So anywhere in your run, if you see, if there's a value A, in this case it was data with the first bit, wants to see who updated this last time. So you just say last, the variable name, and hit enter. It takes you to exactly that point that somebody updated this value the last time. So you don't have to go figure out throughout your code who updated this variable, where was it updated, and whatnot.
Short question in the meantime, is it now running SystemC simulation in the background?
So SystemC simulation already ran. We recorded the SystemC simulation while it ran, and that recording that came out, which is completely portable, I've loaded that recording in our debugger, UDB. When you saw my first command was UDB, and a recording file name with the .undo away. And now this, everything is happening on a non-live system, which represents a live system. So still reversing and still trying to find out, and I can tell you, based on some of the outputs that I saw already in the log, the problem is at the beginning, and it started at the end, right? So it's going to go, make it way backwards and go figure out what happened. Already, I think it's halfway there. It is already telling you that this value, that bit that we were talking about, should have been V.
So the recorded database, that's this date database or more time database?
Both, actually. We introduce the concept of time in your states.
Okay.
So what we're doing is we make a snapshot in the beginning of the recording process of the memory contents, all the address spaces. Then we are keeping a copy of your binary in the assembly level, and we are looking at all the inputs coming into your binary at again instruction level, and we keep track of all that. And now that is enough for us to recreate anything back to you. Obviously, there will be situations where your binary will output something which is non-deterministic. For example, get time of day. Every time you call it, it will be different, so we have to store that too. But if it's A plus B is equal to C, then we do not need to store C. We know the addition operation, we know A and B, so we can recreate C back for you later, right? Oh, cool. Oh, wow. Oh, great. It has already done that, right? As you see, the FIFOs, I mean, I can go a little bit up in my, yes. So as you can see, what went wrong with this program, right? It was supposed to read, this. It was supposed to read the 0th bit, as you can see from the output, but it read the first bit. So the the message was visit accelera.org for more information on SystemC, right? And instead of taking V, which is the 0th element of the word visit, it took I as the element of the visit, and that was actually the problem. So you didn't have to really do anything. I was just talking through it, and it did it, right? And that's kind of what time travel debugging does. So as I said, record, replay, and resolve. The LLM bit that I just showed you is very new. It is just representing what a human would do still. Go to the end of the recording, go backwards, following the data, rather than guessworking what could have happened. You see exactly what happened. Some of the commands that we have for undo. As you must, I mean, how many in this room have actually used GDB? Yeah, a lot of you. Perfect. So you know all the commands: step, next, finish, break, watch, continue, last, right? Not last. So these are all forward functions, as you can see. For every forward function, we have a complementary reverse function. So yeah, reverse function. As you can see, there's a reverse step, reverse next, reverse finish, break is the same, reverse continue, which is very powerful. And then, as I mentioned, the last command, jump to the last time a data or a variable or an address space was changed, which is actually magical. If you're doing memory corruption, the question is always, who wrote to this address space, right? And you do last, and it takes you exactly at that point where the culprit is writing to that space. What we see is that because there are libraries coming from a lot of different places, you don't know, some are parallel, some are not parallel, there could be multi-threading issues, there could be deadlocks, a lot of different things, right? So our technology is applicable to all of this, because what we realize is the major bit is to reproduce this and capture it so you can actually review it again. Every time you use GDB, it's a new run. So the same things may happen or not. I'll give you some examples. So what right now Claude did here in our current example was that it figured out that there is something going on with this part, this variable, or this address location. So we did a last on that, right? And it should tell us who modified it last. And then it reached here, and it said, okay, the new value is 27, which is what we did, and so it just got updated. And now you want to figure out who updated data, because it's coming from data. So you do last data, right? And then you figure out, okay, data is coming from I, but who's giving any I? So you can do last on that, and basically keep going until you figured out what the problem was and the root cause was, right? So that is the model. Now let's just take another one, race condition. So thread 1 red, thread 2 red, thread 1 wrote again, and thread 2 wrote again. So, but we are writing to the same memory location twice, and later at some point somebody will access this and go, wow, that's a garbage value or a wrong value. Who wrote that, right? Has that happened to any of you before? I mean, yes, no. I can see some nods and some no's. Okay. So that's what I said. What we do is record this, replay the recording. The last command is actually a helper function. What it does, it sets a watch point on that hardware location of that variable address space, and then it runs a reverse continue till the watch point is hit, basically. And you can see what changes, what doesn't, and you can identify the missing locking. You didn't have to, by the way, you didn't have to rebuild anything, rerun everything. If you've got the recording there once, that's it. You can query the recording 100 times with different stuff, and you can get all the information that you need. Now let's say it was a deadlock, right? I don't know how many of you actually face deadlocks in your SystemC models. Do you? No? I see one eyebrow raise. Okay, yeah, so I mean, we see, like, sometimes both the parties are waiting for each other and nobody is able to move forward, and that's a deadlock, right? So what we would do again is record it, identify which threads. So we are able to capture all the different threads that were in play, and even if it died later after doing its job, we're able to come and show you everything of time-wise, which thread came, made this change, died, and some other thread came and accessed this, you know, and then you reverse continue through that, and you're able to get to the problem. And sometimes, in fact, it's not mentioned on the slide here, but I'm going to mention it. There are quick and amazing tools like thread fuzzing, because we insert ourselves between the Linux kernel and the application. We can fool the kernel into thinking of a different thread switching context. We can starve threads, we can randomize threads. It's like shaking an apple tree and the apple will fall out. If that doesn't happen, we make a reference recording. We look at all the address spaces that could have been read or written by different threads at the same time. We constrain that even further, and within microseconds, your system fails. And that is a concurrency issue that you didn't even know existed. So, as I mentioned, add time travel debugging in your workflow. One of the ways is to do regressions. So, a lot of our customers, what they do today is they've added a step to their regression pipelines. If this thing fails, rerun it under recording mode until it fails again. And only save the recording if this condition is true, which is a failure, a misbehavior, a certain flag being true or false, right? So by the time you come back in the morning after setting up all these nightly runs, your recording exists. So you don't have to reproduce it anymore, right? And obviously, if you write assertions, we can tap into that. We can know which variable to follow and not. So these are some good best practices that you can follow. And also, it will be good if you add some intermediate variables out there. So we can set different break conditions and run back to that. And one very interesting thing that we made very recently is a waveform viewer, because we realized how important waveforms are to semiconductor firms, right? So from a recording, from an existing recording, you can generate these waveforms, traverse via waves, and let's say you find an interesting point, maybe this one. You click on that, and in the debugger interface, it takes you directly to that one line that has caused this problem, or this waveform. So you can actually track everything in the wave back to your code as it happens. Now it's too good to be true, right? So what's the catch? There is a very small performance overhead that we do introduce. That happens when it's more non-determinism in the code. So for example, I just mentioned get time of day. Every time you do that, it's going to give you a new answer. So we have to save that value. If you do some I/O, if you sort data read, packet processing, you're going to store all that value, and that causes a little bit of slowdown. But if it's computation, then it's like full speed, basically. And obviously, we do require some of these features that I'm assuming most of you guys are working on Linux, and you have backtrace and other things available. Time travel debugging is available in 3 flavors in this world today. One is undo, which is what I showed you a little bit earlier. One is RR. I don't know if you've heard, rr-project.org. It's an open source technology that is being built by one person, Robert, in New Zealand. So it's a good academic tool to use if you are a university student. Has some limitations, doesn't work on VMs, it works only on the latest Intel and AMD processors. But I guess that's really good for academics still, because that's what you're using. And obviously, Microsoft, long ago, built their own time travel debugger. This was supposed to be used by Microsoft employees, but then they are pushing right now Windows to be a development platform. So they made it part of WinDebug, which later became part of Visual Studio. So if any of you is developing on Windows, you can directly access Microsoft's time travel debugger from Visual Studio. Right? And obviously, as I said, each tool will have its own set of problems and all sorts of features that you can choose from. Right? So, if I may ask one of you to answer this question, if you would have debugged that test in your scenario, in your grown-up code base, how much time would it normally take? Like, what is the least amount of time? Anybody? I'm assuming some of you do SystemC already. So you said something. Yeah, okay. So generally we see that it takes at least a day, right? I mean, that's normal. That's how much people take time to fix, backtrack others' code, ask somebody, what did you mean by this line of code? Because they don't understand it. The model was not made by you, being consumed by somebody else. And obviously, so we are very fast. If you use time travel debugging, tracing back from symptom to the problem is really fast. And obviously, we say at least 4 times faster. And like I said, easy to follow data, understand large code bases. So our goal is to de-skill the process. You do not need to be the owner of the code to debug that code. You're able to understand the whole code flow by following the data. And then obviously, it frees up your time to do all these nice things, right? Do coverage, more functional verification, reduce time to market, save your reputation in front of customers who've got a failure. Right? So the conclusion is, you guys should use time travel debugging as much as possible, and I'm happy to help you figure this out. We are at our booth in the exhibition hall, so come see us. We were able to cover what is time travel debugging, what the application is to HLS, how to add it to a regression flow. I even showed how to use Claude to do time travel debugging. And I really hope it helps you guys.